In this example, we're going to solve a second order differential equation with two Dirac functions in them. So we're going to solve x double prime plus 4x prime plus 5x equals delta sub pi of t plus delta sub 2 pi of t, subject to the initial condition that x of 0 is 0 and x prime of 0 is 2. So what's going to happen is we're going to take the transform of both sides. The transform of x double prime is s squared capital X of s minus s little x of 0 minus x prime of 0. The transform of x prime is going to be s capital X of s minus little x of 0 plus 5 capital X of s. The transform of the transform of delta sub pi of t is going to be e to the minus pi s, and the transform of delta sub 2 pi of t is going to be e to the minus 2 pi s. And so now let's put in our initial values. We know that x of 0 is 0, so those terms are gone. X prime of 0 is 2. And so we can do all the usual stuff. Let's take our capital X, and this is going to be s squared plus 4s plus 5 times capital X of s. That takes care of that term, that term, that term. So that's all the terms with the capital X in it. And then let's see, what do we have left? We have minus 2 is equal to e to the negative pi s plus e to the negative 2 pi s. And so that tells us that our capital X of s, what we're going to do is we're going to take the previous expression, add 2 to both sides. So we're going to end up with 2 plus e to the minus pi s plus e to the minus 2 pi s all over s squared plus 4s plus 5. Okay, so this is s squared plus 4s plus 5 and s squared plus 4s plus 5. And one thing you can actually do in the denominator is you can complete the square again. This is s squared plus 4s plus 4 plus 1. The reason we would want to do that, I'll just rewrite it. The reason why we would want to do that will be clear, but we're going to complete the square in the denominator, and this is s plus 2 squared plus 1 plus e to the minus pi s over s squared plus 4s plus 5. Oops. And while that's true, that's not what I meant to write. This should be s plus 2 quantity squared plus 1 plus e to the minus 2 pi s over quantity s plus 2 squared plus 1. Now, what we need to do is figure out how do we take the inverse Laplace transform of these types of functions. And so this is, we're going to use rule number 16. Rule number 16 says that if you take the transform of e to the bt sine of kt, you're going to end up with k over s minus b squared plus k squared in the denominator. So that tells you right away what this first one is going to look like. So this first term, this first fraction here is going to be the transform of e to the negative 2t sine of 1t, so sine of t. The other rule that we're going to need is rule number 30, and that tells us how do we find the transform of shifted Heaviside functions times shifted functions. And so it turns out what happens, and we prove this, is that this is e to the negative as times capital F of s. So you get the transform of capital F times that shifted Heaviside function. Okay, so times that shifted Heaviside function. So we're going to use that rule, and we're just going to have to see what we get here. So let's see. For the first one, we're ready to take the inverse. So for the first one, we're going to end up with 2 times the inverse of that function, which we already said was e to the negative 2t sine of t, because our b is 2, our b is negative 2, and our k is 1. For the second and the third fractions, for the second and the third fractions, for the second and the third fractions, we're going to have to use rule number 13 together with rule number 16. And so if we have e to the negative pi s, that means that our a is pi. So that automatically tells us we're going to have u sub pi of t. And then what we're going to do is we need to think about what's the inverse Laplace transform of capital F. So that's the inverse Laplace transform of this quantity. And that's nothing more than what we just found, e to the negative 2t sine of t. So what we do to that inverse transform is we shift it by pi. So in other words, I'm going to take this function e to the negative 2t sine of t, and what we're going to get is not exactly that, but we're going to get that shifted by pi, sine of t minus pi. And then we'll do the same for the last term. The last term, our a is going to be 2 pi, so we're going to get u sub 2 pi of t, and then e to the negative 2 times t minus 2 pi, sine of t minus 2 pi. Just barely squeezing in our answer there. And you can simplify this if you really want to. I don't care too much. But one of the things that you can do to simplify, if you're into simplifying, is this first part we're stuck with. So sine of t. For the middle two terms, you can use some trigonometry, and sine of t minus pi is minus sine of t. So you can write this as minus u sub pi of t e to the negative 2 times t minus pi sine of t. And if you shift sine by 2 pi, then you're not really shifting at all. So that's going to be plus u sub 2 pi of t e to the negative 2 times the quantity t minus 2 pi sine of t. And that would be our answer.